Looks like it's time. Welcome, everybody. Today, we have a pleasure to have Francis Bischoff, who will be speaking on Lie groupoids and differential equations. Francis, I give you the floor.
Okay, great. Thanks a lot. So thanks to the organizers for inviting me to speak at the seminar, which has had many fascinating talks over the past year. So so what I want to talk about today, it's partly based on a preprint that I put on the archive a while ago. It's also partly based on work which is very much in progress. So although I believe that everything I'm going to say today is accurate, I can't completely guarantee it, so I hope you'll forgive me for that. And also, I'm not an expert on differential equations, so I'm not as familiar with the literature as I'd like to be. So I've done my best to properly cite things, but if you see that I'm omitting an important reference, then it's probably because I'm not aware of it. So I would be grateful if you'd let me know. So let me start. So what is the talk about? So here's the basic idea. So certain differential equations, possibly singular differential equations or flat connections, these can be interpreted as Lie algebroid representations. And these Lie algebroid representations, they can in turn be integrated to Lie groupoid representations. And we can therefore apply Lie theoretic techniques to study differential equations. So this project actually, it goes back to the beginning of my PhD studies under Marco Gualtieri. So I learned about this philosophy of studying differential equations via groupoid representations from him. Okay, so here's an outline of my talk. So it's roughly going to be divided into 3 parts. In the first part, I want to give an overview of this idea of studying differential equations using Lie groupoids and give many examples, in particular the examples that I'm going to focus on later. Then I want to briefly talk about some general Lie theoretic tools which can be useful. And then in the last part, I want to talk about a classification result for flat connections which have logarithmic singularities along reductive free divisors. Okay, so let's start. So for the first part, I wanted to start with 2 representative examples. So here, this is the case of a linear ordinary differential equation on the affine line, which has a Fuchsian singularity at the origin. So here, S is a solution. A of Z is a holomorphic n by n matrix. And this equation, it has a singularity at the origin because of the presence of this Z here. So what this means is that that the solutions, they're possibly going to have a singularity at the origin, and as a result, they could also be multi-valued on the complement. So the main observation here is that such a differential equation, it's equivalent to a smooth representation of a Lie algebroid, which is rank 1. It's generated by this vector field. The way that we can associate such a differential equation to a representation is in the following way. We have a map nabla from the Lie algebroid to GLN, where we send the generator to minus A of Z. And this can in turn be integrated to give a representation of a Lie groupoid like this. Okay, so that's the first example to have in mind. Here's a second example, which is kind of more global. So here, E is a vector bundle over a manifold M. Then a smooth flat connection on the vector bundle E is a map nabla from the tangent bundle to the differential operators, or the first order differential operators on E, which satisfies these 2 equations. So it satisfies the Leibniz rule, and second, the map nabla preserves the bracket. So we can interpret this as a representation of the tangent algebroid. And then by taking the parallel transport of the flat connection, we get a representation of the fundamental groupoid. So this is the groupoid, which consists of paths in M taken up to homotopy. Okay, so these are kind of the 2 prototypical examples that you can keep in mind. Here's the general picture, which is kind of has three parts to it. So here it's the infinitesimal version, or the infinitesimal picture. So given a principal G bundle P over a manifold, we can define its Atiyah algebroid, which is a Lie algebroid of infinitesimal symmetries. It's a Lie algebroid over M, and it sits in a short exact sequence like this. Now, given any Lie algebroid A over M, we can define a representation to be given by a principal bundle along with a Lie algebroid homomorphism from A into the Atiyah algebroid. So the kind of the strategy is that given a flat connection, possibly with singularities, we try to find a Lie algebroid such that the flat connection can be interpreted as a smooth representation of the algebroid. So that's what we did in the first example. We had a differential equation which had a singularity, and we interpreted it as a smooth representation. Okay, the second part is the kind of the more global picture. So the Atiyah algebroid of a principal bundle, it has an integration to a Lie groupoid, which is the gauge groupoid. And the arrows of this groupoid essentially are given by G equivariant isomorphisms between the fibers of the principal bundle. Then, given a Lie groupoid G over M, our representation is defined by a principal G bundle P and a Lie groupoid homomorphism into the gauge groupoid. So what this is essentially doing is, given any arrow in the groupoid, we assign a G equivariant isomorphism between the corresponding fibers of the principal bundle. So this is what happens, for example, when we take the parallel transport of a connection. Okay, so the way that these two pictures are related is through Lie's second theorem for Lie groupoids, which is due to Mackenzie-Shu and Morita-Mercoon. So this just says that if we have G of A, the source simply connected Lie groupoid integrating a Lie algebroid A, then there is an equivalence of categories between the category of representations of the algebroid and the category of representations of the groupoid. And if you look into the proof of this, the way that it works is that we start with a representation of the algebroid, so like a singular differential equation, and we convert that into a smooth, flat connection on the source fibers of the groupoid. And then we take the parallel transport of that. So here, a useful perspective on this is provided by Gualtieri, Lee, Pim. So I've taken this from their paper on Stokes groupoids. What they explain is that the groupoid can be thought of as the universal domain of definition for the fundamental solutions to differential equations. And so even though the solutions to differential equations, they can be singular and multi-valued on M, they become smooth and single-valued on the groupoid. Okay, so now I want to give a couple more examples just to show what different things are possible. So the first example is a generalization of the first example I presented. So this is taken from the paper on Stokes groupoids by Gualtieri, Lee, and Pim. So here we consider a linear ordinary differential equation on the affine line, which has a pole at the origin, but here it can have a pole of order k. So when k is equal to 1, that's the first example I presented. But when k is greater than 1, then the solutions to such an equation, they often have essential singularities at the origin, and their asymptotics, they exhibit this famous Stokes phenomenon. Okay, so what they explain in their paper is that even though this is a very singular equation, they can be interpreted as smooth representations of a Lie algebroid and then integrated to smooth representations of a groupoid, which is what they call the Stokes groupoid. And this groupoid has a very explicit expression. It's as a space, it's C times the affine line, and it has these structure maps. So here's the source, the target, and here's the multiplication. Okay. So it's also possible to generalize this to So this is what they do in their paper. They generalize just the flat connections on a Riemann surface, which have poles along a finite set of points. And a nice example of this that I like is flat connections on the Riemann sphere, which have a second order pole at the origin. These are equivalent to representations of an action groupoid, where it's the action of C by translation on the Riemann sphere. So this has kind of a fixed point of order 2 at 0. Okay, so here's the next example. And this is kind of the main example that I'll be focusing on in varying degrees of generality. So here X is a complex manifold and D is a smooth codimension 1 submanifold. So associated to this, we can define the logarithmic tangent bundle, Tx minus log D. And this is a Lie algebroid over X, whose section consists of vector fields on X, which are tangent to the submanifold D. So we can define a flat connection with logarithmic singularities along D to be a representation of this Lie algebroid. So it's a principal bundle along with a Lie algebroid map from Tx minus log D to be a T algebroid. And so by Lie's theorem, these are equivalent to representations of the integration, the Lie groupoid integrating Tx minus log D, which is the twisted fundamental groupoid. Okay, so I want to generalize this now. So I want to relax the assumption that D was smooth. So I want to consider now the case where D is a reduced and possibly singular divisor in X. In this case, it's still possible to define flat connections on X with logarithmic singularities along D. And in a work of Saito, he defined similarly the logarithmic tangent bundle or logarithmic vector fields, Tx minus log D. But the important thing is that it's defined here as a subsheaf of vector fields on X, and in general, it's not locally free. So we don't get a Lie algebroid for a general singular divisor. But what Saito did is he kind of identified a special class of divisors, which are called the free divisors. And these are defined by the property that the logarithmic tangent bundle is locally free. So it does define a vector bundle. And so in this case, we do get a Lie algebroid. And then by a theorem of Claire-Debar, this Lie algebroid is integrable, and so it defines a twisted fundamental groupoid, which we can use to study these flat connections. Okay, so Saito, he gave also a really useful criterion, which is easy to check in practice, for determining whether a divisor is free. So what he says that you have to do is the following. You're supposed to take n vector fields which generate this sheaf, and then you wedge them together like this, and then you divide by a volume form, and this will give you a function f. And the theorem is that that this divisor is free if and only if this function f is a reduced equation for D.
The volume form, you mean the volume element, or so you mean that this volume?
I just mean just take some local coordinates and then take like.
Okay.
Another way of saying it is if you write these vector fields in terms of a basis of vector fields, then you take the coefficients and you take their determinant, then the condition is that that function, it should be the reduced equation for D. Yeah, that's right. This is dual to a volume form, I guess. Yeah. Okay, so yeah, so there's plenty of examples of these. Here's just one example. Well, any reduced plane curve is a free divisor. So here's an example. The vanishing locus of this function, x squared minus y cubed. This is a singular divisor. It has a cusp at the origin, so it looks like that. So the logarithmic tangent bundle, in this case, it's locally free, and it's generated by two vector fields, E and V. And if we take their Lie bracket, we see that the bracket of E and V is V. And so therefore, the logarithmic tangent bundle, it's actually isomorphic to the action algebroid for a Lie algebra acting on C2. So you might at first expect that the twisted fundamental groupoid will be an action groupoid, but this is not the case because V is not complete. The way that you can see this is as follows. So here, F equals to 0, which defines D, but we can consider F equals to another constant, and that defines a family of punctured elliptic curves like this. The vector field E, it kind of acts by moving us from one elliptic curve to another, whereas the vector field V, it's a vector field along the elliptic curve. And so because this curve is punctured, V is not complete. So the twisted fundamental groupoid is a little bit more complicated than you might expect, but I think you can think of it as describing symmetries of this family. Okay. So now I want to focus on a special class of free divisors. So these are due to Buchweiz and Mond. So they first of all introduced the notion of what's called a linear free divisor. So this is a divisor, a free divisor in a vector space C to the n, but it has the property that the generators are linear vector fields. Now, because if you take the Lie bracket of two linear vector fields, it's a linear vector field, that means that they give you a Lie algebra, which I'm calling GD, which lies inside of GLN. And then the logarithmic tangent bundle, it will be an action Lie algebroid for this Lie algebra. So this divisor is called a reductive free divisor when this Lie algebra is a reductive Lie algebra. In this case, the twisted fundamental groupoid, it will be the action groupoid, where G is the universal cover of a complex reductive group, which is acting linearly. So there's many examples of these. One of them is the normal crossing divisor. So this is the union of the coordinate hyperplanes. In this case, the reductive group would be a product of C stars, an algebraic torus. And so the universal cover is C to the n. Another nice example is the discriminant in the space of binary cubics. So here the space is C to the 4, which we're thinking of as the space of homogeneous cubic polynomials in in two variables, u and v. So the coefficients are x, y, z, and w. Then the divisor here is the space of cubics which have repeated roots, and it's defined by this discriminant. So in this case, the reductive group is GL2. So Buchweiz and Mond and other authors, they construct a whole bunch of examples of reductive free divisors. In particular, they construct a bunch that come from representations of quivers. Okay, and just as an aside, I just wanted to mention that it's possible to kind of generalize the construction of the Stokes groupoid from the paper of Gualtieri, Lee, Pim to describe a groupoid which presumably will describe flat connections which have irregular singularities along reductive free divisors. So I've just written it out here for the case of the discriminant in the space of cubics. So here H is the discriminant function whose vanishing defines D. And we can define a groupoid where the total space is C times SL2C times C to the 4, and it has these structure maps. So the key thing is that here we have H is involved in the formula. So this is kind of a generalization of the Stokes groupoids. Okay, so to end the first part, I just maybe speculate a little bit on, well, if we're interested in studying singular flat connections via Lie algebroid representations, what is the kind of the appropriate class of Lie algebroids that we should consider? So one option is that we could study Lie algebroids A, which have a dense orbit, and such that the restriction of A to this orbit is the tangent bundle. That's one possibility. In fact, it makes sense to consider something slightly more general where we don't require this last property. We just consider Lie algebroids which have a dense orbit. And the reason why this might be interesting is that the isotropy, you can use it to encode the curvature of a connection. So here's just one example of this. If A is a transitive Lie algebroid, so it sits in this exact sequence. So G here is the kernel of the anchor map, and it's a bundle of Lie algebras. If we choose a splitting sigma, then if this splitting doesn't preserve the bracket, it will have a curvature, which is a two-form valued in G. And so using this splitting, we can convert any representation of A to a connection for the tangent bundle, but which has a curvature given by omega. Okay, so yeah, so in this section, I just want to kind of briefly mention some general Lie theoretic tools that can be useful for studying representation. So the first one is Morita equivalence. So Morita equivalence is an equivalence relation between Lie groupoids, which is more general than isomorphism. If you want, two groupoids are Morita equivalent when they represent the same quotient stack. But there's a concrete definition, which is given as follows. So a Morita equivalence between groupoids G and H, it consists of a space Q, which maps to the base of the two groupoids, and it's equipped with two actions, an action of G on the left and an action of H on the right, and both of these actions are kind of compatible and both principal. So the reason why a Morita equivalence is useful is because of the following theorem, which says that a Morita equivalence between two groupoids, it induces an equivalence of categories between their categories of representation. So this can be useful because maybe we're interested in the representations of G, which is kind of intractable, but we can replace it with a Morita equivalent groupoid, which is a little bit easier to handle. So the canonical example of this is the case of the fundamental groupoid of a manifold. So here the statement is that the fundamental group of a manifold at a base point X is Morita equivalent to the fundamental groupoid. And so in this way, we can recover the classical Riemann-Hilbert correspondence. So on the left here, we have flat connections, which are representations of the tangent bundle. By Lie's second theorem, they're equivalent to representations of the fundamental groupoid. And then by Morita equivalence, these are equivalent to representations of fundamental group. A similar example along these lines is the equivalence between projectively flat connections and projective representations of the fundamental group. So here, the setting is we have L, a line bundle over a manifold, which has a degree C1. Then its Atiyah algebroid is a transitive Lie algebroid, like this. So just as before, if we take a splitting, sigma, so this will have a curvature, omega, which represents the degree of the line bundle. And this produces an equivalence between representations of the Atiyah algebroid and connections for the tangent bundle, which have a central curvature like this. And now this groupoid is Morita equivalent to a group, which is a central extension of the fundamental group. And so we get an equivalence between the connections which have central curvature and representations of this central extension of the fundamental group. Okay. So the next useful technique is linearization. So what this is the following. So let's say we have a groupoid G over a space X, and Y is an orbit of the groupoid, and U is a neighborhood of Y. Then a linearization is an isomorphism of groupoids between G restricted to this neighborhood U, and a linear approximation which I've written here as the restriction of the groupoid to the orbit acting on the normal bundle to y. So there's quite a large literature on linearizations. So I've tried to list several of the people who've written about this, but no doubt I've left out some people. So this is usually stated in the smooth category, but it makes sense in the holomorphic category. There's just one thing which you have to kind of watch out for, which is that a linearization, it's kind of underlying it is a tubular neighborhood embedding. And these don't exist in the holomorphic category in general. So in the holomorphic category, we should replace an isomorphism by a Morita equivalence. So in fact, in the smooth category, there's a result of Weinstein, which states essentially that having an isomorphism and a Morita equivalence in the setting is equivalent. In the holomorphic category, it's no longer equivalent. We should go with the weaker notion. Okay, so here's a result for when you have a complex manifold and a smooth hypersurface. So this kind of combines linearization and Morita equivalence. So first of all, if we have a complex manifold X with a smooth hypersurface D, and U is a tubular neighborhood, then there are Morita equivalences between the twisted fundamental groupoid of the neighborhood and a linear approximation. And in fact, there is a further Morita equivalence to an action groupoid for the linear action of a group on the affine line. And furthermore, using kind of a Van Kempen type result, you can prove that the twisted fundamental groupoid of X and D is Morita equivalent to a groupoid, which is kind of a push out or a coproduct of the fundamental group of the complement of D and X and this action groupoid. And the significance of this result is that it implies that the study of logarithmic flat connections on X with singularities along D, this gets completely reduced to studying the representations of the fundamental group of the complement and linear ordinary differential equations with Fuchsian singularities on the affine line. So in this way, we can recover classification results due to Deling, Simpson, and August for logarithmic flat connections. But an important advantage of using groupoids is that everything is automatically functorial. And I think this is kind of, you could think of this as maybe a template for what we could do in more general situations of Lie algebroids. Okay, so just a couple of final comments about linearization. So in the smooth category, linearizations, they usually only exist for proper groupoids. So those are groupoids that have some type of compactness property. In the holomorphic category, we should also not expect linearization to always exist. We should expect them to hold maybe when the isotropy groups are reductive, at least for an adjoint form of the groupoid. And there is some work by these authors which seems, so I don't quite understand their paper, but it seems to have a result like this in the algebraic category. Okay, so so I had these two examples of groupoids before, and both of these groupoids, they were not linearizable, and not coincidentally, they have non-reductive isotropy groups. So we can already see here that the presence of reductive groups should simplify the study of differential equations. So in the final part of my talk, I want to kind of further explain this by giving a classification of flat connections which have logarithmic singularities along reductive free divisors. So here's the scenario for this. So we want to classify flat connections on C to the n which have logarithmic singularities along a reductive free divisor. So here are three important examples. So this is maybe the most important. So this is the case of linear ordinary differential equations with Fuchsian singularities at the origin. So there's extensive literature on this. I've tried to name some of the important people who've worked on this. Another example is this case. So this is the case of logarithmic singularities along simple normal crossing divisors. And these have been classified by Deling, Yoshida Takano, and Bollybrook. Another example of this is the one of the discriminant in the space of binary cubics. Not aware of any work on this example. Yeah, and one thing to keep in mind is that the study of these equations is often based on the use of power series solutions. So I want to explain an approach to classification which is more geometric. Okay, so here's the general setup. So we have D inside of C to the n, a reductive free divisor. So recall, in this case, the logarithmic tangent bundle, it's given by the action of a reductive Lie algebra, G sub D. And this reductive Lie algebra, it can be decomposed into this abelian part, which is the center, and a semi-simple part. So this means that the twisted fundamental groupoid integrating the algebroid is given by the linear action of a group, which is the product of C to the K and a semi-simple simply connected group. Okay, and so what we're interested in is classifying representations, which roughly speaking are homomorphisms from this groupoid into GLR. So it's not essential to have the general linear group. We could replace it with any reductive group. That's fine, but this is, I'll stick with this for simplicity. Okay, so in order to explain how I'm going to think about classifying these, I need to explain the notion of linearization of a representation. So given a representation phi of this groupoid, one thing that we can do is we can restrict it to the origin in C to the n. And when we do this, we get a representation of a group. And this is equivalent to the representation of this Lie algebra G sub D. Conversely, if we have a representation of this group, then we can produce from it a very simple representation of the twisted fundamental groupoid. Given by the following formula, notice that it doesn't depend on where we are in C to the n. So it's kind of like a constant representation. So it's very simple. So now if we're given a representation phi, we can combine both steps. So we can first of all extract a representation of a group, and then we can produce out of that a very simple representation of the groupoid. And this here we'll call the linear approximation. And so the goal in the classification of representations is to find a linearization isomorphism between our given representation and its linear approximation. Or at least if we can't do this, we'd like to characterize what are the obstructions to doing this. So in fact, there are obstructions to doing this. Not all representations can be linearized. So in order to explain this, I need to explain the monodromy. So here again, we have a representation of the groupoid. And now given any element, n in z to the k, so I'm thinking of z to the k as a lattice inside of this abelian group, c to the k. So the points in this lattice, when they act on c to the n, they act trivially. They're completely contained in the isotropy. So that means that associated to any one of these elements, we can define a monodromy, which is defined by this formula. And it assigns to every point in the base an element of GLR. And so each of these Mn, they define automorphisms of the representation. And in fact, they all commute with each other. Now, the fact that they are automorphisms of the representation, this means that on any orbit, one of these monodromy elements, when we restrict it to a single orbit, it will lie in a single conjugacy class. Then, because in this case, the group that's acting, it has the groupoid that's acting, it has a dense orbit. That means that the image of one of these monodromy maps, the image will lie in the closure of a conjugacy class. And this is an important point because it could be the case that the value of the monodromy at some point z and the value at the origin, they might not be conjugate. And this represents an obstruction to linearizability. The reason for this is very easy to see. If we go back to the slide here, so for one of these very simple representations, we can see it doesn't depend on z. And so that means that the monodromy of one of these things, it doesn't depend on z. So that means that if we have any representation which is isomorphic to its linear approximation, that means that the monodromy, it should stay always in a single conjugacy class. Okay, so this is an obstruction to linearizability. And the theorem is actually, this is the only obstruction to linearizability. So here's the theorem. It's kind of two versions. So first of all, if D is an irreducible reductive free divisor, then a representation is linearizable if and only if the monodromy over a generic point is conjugate to the monodromy over the point 0. If we have a general reductive free divisor, we can say something a little bit weaker, which is that a representation is linearizable if the monodromy is semi-simple. So let me just explain this in the special case where we have a linear ODE on the affine line with a Fuchsian singularity at the origin. So in this case, this says that this ODE, it's gauge equivalent to one of the form like this, where we've replaced a of z with a constant a of 0, if and only if the monodromy of this equation is conjugate to the exponential of minus 2 pi I a of 0. Yeah, and so this is a result which I'm pretty sure it should be contained in the literature. I haven't been able to find a reference, so if anyone knows a reference of this fact, I would be very grateful if you could let me know. Okay, so I'll present a sketch of the proof. So here's the two things that we have. We have a given representation, which satisfies the conditions of the theorem. And we have here the linear approximation. The goal of the theorem is to find an isomorphism between phi and f. And concretely, what this means is that we want to find a map H from C to the n to GLR, a holomorphic map, which conjugates phi to f. And one way of expressing it is the following equation. The way that we can think of this is as follows, is that this group here, it acts on GLR on both, on the left, using phi, on the right, using f. And with respect to this action, we want to find a function h, which is invariant. So that's the goal. So the way that we're going to produce this is according to the following steps. So first, step one, and this is the part that relies on the assumptions. Is that we conjugate phi so that the monodromy is constant and is equal to the monodromy of this linear approximation. So here I'm kind of sweeping some things under the rug. You can really only do this locally around the origin in c to the n, but I'm going to kind of ignore that just for the purposes of the presentation. Okay, so now that we've done this, we can define C to be a subgroup in GLR to be the centralizer of all of the monodromies. Okay, and then we can define an action of this group on the bundle C times C to the n, which is exactly given the one that I just discussed, where we act on the left by phi and on the right by f in this way. And so now this is the key fact, which is that because phi and f, they have the same monodromy, and C is in the centralizer of the monodromy, that means that the action of the monodromy, so the action of z to the k, it acts trivially. And so that means that this action, it descends to an action of C star to the k times S. So now we have the action of a reductive group. And so we can apply all the kind of the great stuff about actions of reductive groups. So what we do then is we can linearize at the fixed point, which is the identity in C and the origin in C to the n. So what this means here, so I've drawn a picture. We have this bundle C times C to the n, projecting down to C to the n. Here's the fixed point, which is the identity in C and the origin in C to the n. In green here, I've drawn the tangent space. And we have kind of a local isomorphism between, a local equivariant isomorphism between the action of the reductive group on the bundle and the action on the tangent space, which is a representation of the group. And this, it sits in a short exact sequence of representations. Because here, the fiber above the point 0, this thing is fixed by the action of the group. And so its tangent space gives you a subrepresentation. And then the quotient is the tangent space to the base, which is another representation. And so remember what the goal was. We want to find this map H, which is invariant under the action of the group. So what this means really is that we want to find a splitting, a map like this. So this means what we're trying to find is a splitting of the sequence of representations, which we can do because they're representations of a reductive group. So that finishes the proof. Okay, so what this result shows, if we look back, is that really the obstruction to linearizing a representation, it lies in the monodromy, but more specifically in the unipotent component of the monodromy. So the monodromy is an invertible element of GLN, and we can use the Jordan decomposition to write it as the product of a semi-simple element and a unipotent element. And it's this unipotent element which is really causing us problems. So if we want to do a classification, the next step is to kind of untwist this obstruction. And we can do this using groupoid cocycles. Okay, so there's a construction of this. So the first thing is that we can construct a homomorphism from this lattice Z to the R to the automorphism group of the representation. And what we do is we just take the monodromy, which was an automorphism, and we take its unipotent component. That still gives us an automorphism. Then, using this, we can construct the following map. It's a map sigma from the groupoid to GLR, And it's constructed with this formula, which involves logarithms and exponentials. But the important point of this is that this gives us a groupoid one cocycle. And what this means is that if we compose it with the representation, we get another representation. And the important fact is that this representation now has semi-simple monodromy, which means that it can be linearized. So this, it can be repackaged in the following form, which is kind of a Jordan decomposition for groupoid representations, or if you want, for logarithmic flat connections. So I want to define a category here where the objects consist of tuples, psi u, where psi is a representation of the groupoid, which has semi-simple monodromy, and u is a map from z to the k to the automorphism group of this representation, whose image consists of unipotent elements. Okay, and then the theorem is that this construction, I mean, these two steps that I just described, they kind of combine to give us a functor, which is an equivalence of categories between the category of representations of this groupoid and this category JC. So I think of this kind of as a Jordan decomposition for connections. And in fact, in the case of ordinary differential equations with Fuchsian singularities, an infinitesimal version of this result is due to Lavelt and Turitin. For them, I believe, though, it follows from their classification results, whereas in my case, it's being used to prove the classification result. So the logic is kind of flipped here. Okay, so the upshot of all this is that we can get a classification. So a representation of this groupoid, or in other words, a flat connection with logarithmic singularities along a reductive free divisor, is classified by the data of tuples f and u, where f is a representation of this group, or equivalently a representation of the reductive Lie algebra, whose restriction to c to the k is semi-simple. And u is defined to be a homomorphism from z to the k into the automorphism groups of the associated groupoid representation, whose image consists of unipotent elements. So from this point, it's possible to kind of further massage this into kind of a nicer statement of the classification. So that's certainly possible, but I think kind of the main work is already achieved. So I'm just going to leave it at this. And then I just want to comment on two more things. Okay, so the first is about resonance. So this is something which shows up when you study differential equations with Fuchsian singularities. And it's really the main source of subtlety and confusion in the study of these differential equations. And so I kind of want to explain a point which I think is probably well known to experts, but at least for me, when I was first trying to learn this, it took me a while for this to kind of sink in. So I want to start with an example. So here's an ordinary differential equation on A1 with a Fuchsian singularity at the origin, the 2x2 system. And the monodromy of this system of equations is given by this. So we can see here that at z equals to 1, it's upper triangular, and at z equals to 0, it's the identity. So these two monodromy matrices are definitely not conjugate. And so as a result, this ordinary differential equation is not linearizable. So the reason, the cause that's usually attributed to the failure of linearizability, it's usually attributed to resonance, which is the fact that the eigenvalues of the residue, so the residue of this is this matrix, that's the residue, And the eigenvalues of the residue, which are 0 and 1, they differ by a positive integer. And that's usually cited as the reason why this differential equation is not linearizable. But a minute ago, I've just explained why that the obstruction to linearizability is actually lies in the unipotent part of the monodromy. So I want to explain kind of how these two things fit together. So let's take here a representation of a group and take the associated groupoid representation phi. Then the automorphism group of this groupoid representation, it lies in a split short exact sequence. So here is the automorphism group of the representation. It projects to the automorphism group of the group representation. This has a splitting, which I'll call, say, P. And the kernel here is a unipotent group. Now, making use of the classification that I just explained, the extra data that you need to specify a groupoid representation or a differential equation is the data of a map of a homomorphism from Z to the K to the automorphism group with a unipotent image. Now, we can see that essentially a representation, which now we're just specifying it by this map U, it will be linearizable if and only if this map U can be conjugated so that it lies completely in P. That's the condition for it to be linearizable. And the relationship to resonance is the following. A representation, it has a resonance precisely when this unipotent group here is non-trivial. So when this group is trivial, then any map like this, which lands into the automorphism group of phi, it automatically lands in the automorphism group of F because the two groups are equal. So when there's no resonance, all representations are linearizable. But when we do have resonance, then there is a possibility that that we have a non-linearizable representation, because it's possible to map into this group in such a way that the conjugacy class doesn't land in the automorphism group. For example, if we mapped completely into here, then for sure that would not be a linearizable representation if it was non-zero. Okay, so that's what I wanted to say about resonance. And as the last thing, I just wanted to explain how you can kind of get a normal form for flat logarithmic connections, kind of in terms of like the infinitesimal data. So for this, so a flat logarithmic connection, it has the form nabla equals d minus omega, where omega is a one form, is a logarithmic one form with values in the Lie algebra GLR. And we can make this identification that this logarithmic one forms are equivalent to functions valued in the dual to the Lie algebra, and this decomposes into the kind of the central part and the semi-simple part. And I'm going to pick a basis of one forms corresponding to a basis of Z to the R. Then the normal form in this case is the following. It says that given any connection like this, we can find a holomorphic gauge transformation which converts it into the following form, omega prime, where now, so this part and this part is the kind of the linear approximation part. So rho is just a representation of the semi-simple Lie algebra. These SIs, which you see they're multiplying these one forms, these are mutually commuting semi-simple elements which centralize rho. And then finally, the last part is the resonant part. And this part, you see, it depends on c to the n, so it's not linear. And we can think of it in the following way. So it's a polynomial valued in the Lie algebra. And these terms, they're all mutually commuting, nilpotent elements. And they're invariant with respect to an action of this Lie algebra. So this Lie algebra, it acts on the base, c to the n, and therefore it acts on the polynomial ring. And through this representation, the linear approximation, it also acts on here. And so the resonant terms are going to be invariant elements inside of here. Okay.
Francis, is it easy to see why these resonant terms should be polynomial instead of just arbitrary holomorphic functions?
Yeah, it's the so you can think of it like, so n, I can think of it as a map, so NEI, it's a map from, let me write it like this, the symmetric algebra of c to the n completed, if you want, that would be like the power series, to GLR C. Now this has a representation of the reductive group, and this also has a representation of the reductive group. And essentially, we want to send. I mean, this thing will decompose into the irreducible representations, and so will this. And so the irreducible representation, like the only terms that are going to show up here that are going to be non-zero are going to be the ones that are the irreducible representations that correspond to the ones inside of this representation. And in particular, we have at least one action of C star, like a torus. So this action of C or C star is going to have some weights in this representation here. And so that means that if we kind of go up high enough in the symmetric power, we're going to get to a larger weight. And so that's why it can't map in. I don't know if that's clear. But
yeah, that helps. Thank you.
Yeah. Okay, so I think that that's all that I have. I guess one kind of, yeah, I think that's it. I'll end it here. Thanks.
Thank you, Francis. Please, questions or comments? Maybe I have a naive question. So if we go back to that Stokes phenomenon on the affine line, so how would the classification play there? What's happening if you have those Stokes groupoids with z to the k d over dz instead of z d over dz? So what's right? How would your classification look like?
Yeah, so I guess the answer here is that it wouldn't work, and the reason is that the Stokes groupoids, they kind of involve non-reductive groups.
Mm-hmm.
So this one is not algebraic, but there is an algebraic groupoid, and if you look at the isotropy group there, it's a unipotent group.
Mm-hmm.
So it seems really that the division between differential equations which are easy to solve and differential equations which are difficult to solve is exactly the distinction of whether the isotropy group is reductive or not. So I think if you wanted to tackle this case where we know, I mean, these things are classified, but it's a much more complicated classification. And I think you would really need to deal with the fact that you have a reductive group, or sorry, a non-reductive group.
Mm-hmm. Okay, thank you. Are there?
Yeah, I have a question.
Yeah, please go ahead.
Yes, so this goes back to the very beginning of your talk, as I understand it. You look at a divisor and look at the vector fields tangent to the divisor, which means those which annihilate the functions of which the divisor is the vanishing set. And then you call the divisor free. I think that was the word.
Yeah.
If that's a free module, if it's a free module. So in the suppose you have, if you drop the free assumption, then we don't get a Lie algebroid, but I think that one still has a Lie-Reinhardt algebra, meaning that you still have this I guess sheaf or module of vector fields closed under bracket. Is there anything interesting you can do in that more general case?
Yeah, that's a good question. So even when it's not free, it's actually not that bad. I think Saito proves it's coherent, reflective sheaf, whatever that means. But so it has some nice properties. And I guess like you could expand your definition of Lie algebroid, like you said, to include this. I guess the thing for me that I don't know what to do is I don't know how you would integrate it.
Yeah, that's what is going to be the next question. I don't know if there's any. I mean, something I've been doing completely different from this has also led to some Lie-Reinhardt algebra, and I'm wondering if anyone has thought about what the groupoid equivalent is. It could presumably be some kind of a singular Lie groupoid.
Yeah, that's a really good question. Yeah. Yeah, so I guess it has a resolution. Dima in the comments said it has a resolution by a higher Lie algebroid, like an L infinity algebroid. So I guess in those cases, maybe you could integrate it to some higher groupoid, I guess. So maybe maybe there's something interesting that you could do in those cases as well. Yeah, but I haven't really thought about this too much.
Okay, thank you. Other questions or comments? If not, Francis, thanks again. So next week, I would like to remind you that will be Zheng Hua speaking, and it will be on a different schedule on how we formulate it now, Eastern Hemisphere schedule, and it will be 3 hours earlier than the slot that we have today. So of course, it's highly inconvenient for the US West Coast. It's much more convenient for places in Asia. So next time we'll be on this Eastern Hemisphere schedule. Well, thank you everybody for participating. Thank you, Francis, for your nice talk. And well, we see you next week on Global Poisson. Bye.
Thanks, Francis. Thanks, Anton.